record this. Okay, last lesson. So we'll review on Thursday for your test next Tuesday. The review is already up online. Then we'll review next Thursday for the final, and then your final is the 14th of May. If you were one of the ones that have the 90s on all your tests, I will grade your test on Wednesday morning, and I will send you an email if you have to show up for the final review. If not, you get to skip the final review, and you'll be done next Tuesday. Yes.
What day is our project?
The 7th. Next Thursday. So
Final exam.
May 14th. Yes.
And do we just email you our project?
Yep, you can just email it to me. That's fine. All right. So in essence, 10.3 is very similar to 10.2. We're just using mean. The only other difference is we have to be using the t-score for it and not the z-score because we don't know the population information. We only know the sample information. So a couple of things that we need to make sure of first. Sample has to be obtained by a random sampling or a randomized experiment. It should contain no outliers. So we can't have any outliers in the data. If you do, you remove the outliers. And the population from which the sample is drawn is normally distributed, or the sample size is large, more than 30 pieces of information. Sample values are independent, and that it's less than 5% of the population. So those are pretty much the same as the proportion, except that there's no outliers in the information, and we have to have a large enough sample. So the mean, we use the mean symbol. So I'm going to have the mean. So same thing, my null hypothesis and my alternate hypothesis. My null hypothesis is always equals. My alternate hypothesis is greater than, less than, or not equal to. So same process as the proportion. Still need to select our level of significance. So normally, like I said, it's 0.05, but you can have 0.01 or 0.10. And then we're using the technological approach. So the p-value, so you're actually going to compare it, same concept as before, the two-tailed, the left-tailed, and the right-tailed. So we're going to compare our p-value to what the significance level was. All right, let's do it. Huh? Well, and that's actually one of the things that in these problems, there's going to be a lot more numbers. So, okay, so there'll be a lot more information in the problems to be able to pull things out. So, all right, take a minute, read the problem. All right. So sometimes in these problems, I actually think it's easier to pull out the sample data first. So what's the sample mean? 176.46. What's the sample standard deviation? Yep. And how many people did I look at? Or how many people were in the study? 70. And what's my level of significance? Okay, so now we've used that number, that number, that number, and that number. So that's the number for my hypothesis. Okay? Because what I've noticed is a lot of times when that number, the hypothesis number is the hardest number to find. If you try to find that first, because you still have all the rest of the numbers, we start eliminating all the other numbers because they make sense for other things. The hypothesis number sticks out. So that is the population that we're going to be comparing it to. So my null hypothesis is 242.64. And what are we saying? We want to say less than, greater than, or not equal to it. Yeah, we want to say it's less than that, right? So we're saying our mean is going to be less than that. All right, so let's see. So this calculator is 33. So my sample mean is 176.46. 163.56. 242.64. And level of significance is 5. And we're looking at less than. So you'll notice in this one, we've got our null hypothesis, our alternate hypothesis. That's the way it was. You'll also notice that we have the degrees of freedom because this is a t-test. So we have our degrees of freedom in there. The sample mean should match what your sample mean is. The standard error, remember the standard deviation is that taken divided by the square root of n. So we're taking the 163.56 and dividing it by the square root of 70. And my critical value is my t-value is plus or minus 1.6672. That they calculate for you. The test statistic is going to, so the t-value here, that's my critical value. That's based on the 5% or the 0.05. My test statistic is based on my information. So the two methods that we can use to compare it, the classical method, we're going to compare this to that. And then the p-value, we compare the p-value to the 0.05. So, yes. Because I don't know the population standard deviation. All right, so visualized, it's way down here. So my test statistic is negative 3.38, which is less than the 1.667. And my p-value is 0.006, which is definitely less than 0.05. So I am rejecting the null hypothesis in this situation. Oh, go ahead. What do you need? I can make bigger. So the t-value, the critical region is t is less than negative 1.667. And the t-value that I got, my test statistic is negative 3.3853. so we've rejected. So, what's my conclusion? Yeah. The mean monthly debt payment in Wyoming is less than that in the United States. It is less. That's why we rejected the null hypothesis. The average student loan payment in Connecticut is $351. They don't give me the standard deviation, so we can't do the actual calculation, but we're on the high end. So they all had a bachelor's degree, so all went to college. So that's one of the things to actually look at. So, all right. Easy enough? Huh? Oh, yeah. They're always, you know. All right. Let's look at this one while you're reading. I'm going to do some typing. Oh, darn it. That's not what I wanted to do. That's what I wanted to do. All right. So they're trying to figure out if they're selling the candy bars are the correct weight. So the manufacturer calibrates the machine so the mean weight is 20.1 grams. And the Snicker bar is supposed to weigh 20 grams. Okay. So they got the random sample of 11 candy bars. Should the machine be shut down and calibrated because shutting down is very expensive? He decides to conduct the test at the 0.01 level of significance. All right, so what makes this one more difficult, or what makes this one different? Huh? Okay, so kind of. So it's supposed to weigh 20 grams. They've set their machine to go at 20.1. So this way, figuring that if they're over it, it's a less likely chance that it's going to be under the 20 grams because they would get in trouble if they're selling things that are light. So they would rather it be overweight than light. So we're not going to use the 20 grams actually is more just for information. We would use the 20.1 grams in that situation. So your mean, your null hypothesis and alternate hypothesis is going to be based on the 20.1. And then my alternate hypothesis is going to be what? Less than, greater than, or not equal to? We don't have a sample mean yet. That's the second problem in this. We'll get that in a minute. No. No. I'll show you how to get the sample mean in a second. Are we looking at less than, greater than, or not equal to in this problem? What do you think?
I could argue it either way. Less than or not equals to.
Yeah. So they're making a penalty if they sell it under their advertised weight. So I would say I would do less than in this case.
Unless they're worried, concerned about the calibration. But what if it's putting out bars that are 20.5?
Yeah.
So then we would do not equals.
Yeah.
But yeah.
The way that, like, yes, you could make an argument either direction, and they're probably we can do it both to see if it actually makes a difference. I would say in this case, because this is written there, I would say I would look at less than because of that statement. If that wasn't there, if they were just looking at the calibration, I would go the other direction. But the wonderful thing of English, you never quite know. All right. And since I cut out all the other slides that had the answer on it, I couldn't tell you what their answer was. Now, in this problem, they don't give you the sample mean and sample standard deviation. What do they give you? Nope. They do give you a hypothesis, yes. Yeah, they give me the table of 11 candy bars. He randomly grabbed 11 candy bars off the line and weighed them. Okay? So we've got 11 candy bars. All right? So what's the problem based on the rules for hypothesis testing? Let's go back and look at the pieces of things that I need. Yeah.
What was the sample size again?
11.
What's the population?
Didn't tell us what the population was. No. The 11's the issue. We need to know if it's normally distributed or we have more than 30. I only got 11. So you really have to show that this is normally distributed. And I probably should actually put that in this. I will fix that for next time. Between classes. I'll actually add a box in here that actually tests for normality. So to determine normality, I have one. I'm just going to put it in the case of the other one. Oh, that's not what I wanted. That's regression. Where's my normal calculator? There it is. A26. So calculator A26 will actually test if the data is normal. So in this case, what it does is it compares your correlation to your critical value when it's doing it. And so in this case, the data points are there, and the data is likely normal because my correlation is higher than my critical value that I'm looking at. This is the chapter 4 stuff we didn't do. Okay, this is all in chapter 4 that we didn't cover. So for most situations, you can assume that it's normal when you're doing it, unless it looks like really crazy. For the homework, you can assume that it's normal because they wouldn't give it to you if it wasn't normal. But this actually calculator is there. I'm actually going to build this into that other calculator. I'll fix it. So that actually will test the normality and tell you right there if it's normal or not. So we put our data in. In this case, since I don't have the data, I type in all the data. It then will calculate your mean and your standard deviation and your degree of freedom. My hypothesized mean for this one is 20.1. And we're doing a 0.1 level significance, and I'm worried about it being less than. Actually, I was going to say, actually, if we're looking at less than, this should be 20, not 20.1. Let's see what the book says.
The book, I just looked at that. The book says not equal.
Because it's looking at calibration.
And it says 20.1.
Right. So we'll actually do them both, because actually this one, I can see it both ways, and actually there's a reason for this. We'll do the book one first, and then I will show you why I think the other direction for the other one. So we'll say this is not equal to, which is fine. And then I'll say why I think we could do the other one too. Because the other one I actually think is more important. Because they're checking, so the way the book is looking at this problem is they're looking to make sure the machine is calibrated correctly. Is it giving you the 20.1 that should? Okay, that's what they're caring about. So in this case, that's my value there, and we're going to reject. Because it's not in, we're not rejecting, we're failing to reject the null hypothesis. Which means, if we're failing to reject that, what does that mean in terms of this problem? If we're failing to reject the null hypothesis. Is the machine working fine? Or do I need to shut it down? You do. We do have some values that are under the 20. And we have some values that are over the 20. Significantly over the 20, actually, in some of them. So that's the question. So this is what this is testing. This is saying, so you don't want to look at, we're looking at the set of 11 that I pulled. Okay? So 20.1 is right in the middle. So we're above that 20.1 in that respect. Okay, so we're above that 20.1. So, but are we so far above it that I should shut the machine down? No, because I'm not in those regions at the end. So we are failing to reject the null hypothesis that it is different than the 20.1. So the machine is calibrated correctly based on my data. Now, the one that I was saying is if we're looking at the fact that I would be penalized if it's less than 20, that's what I would test. I don't care if it's 20.1. I'm testing to make sure that they actually come out to be above 20. Because if they come out, the average is under 20, then I'm going to be fine. Okay? So I would test that case, which is also going to fail to reject. And that also fails to reject substantially because it's even further over. Okay. Now, your question, your statement is very true. If we look at this table of 11 Snicker bar things, are there some that are lower than 20? Should they be fined? Is any inspector going to figure that out? How do you think they test for weight? They take a bag or a case and weigh it. They're not testing individual bars. They're going to take a bag of them and weigh the bag. And as long as that bag falls within a certain range or the case falls within a certain range, we're fine. Okay? Because they're not pulling out individual ones to test. So yes, there's a couple that are under, but those couple that are over balances it out. Because the probability that you're going to have a bag with all of them being under would be statistically unlikely. You're going to get that range, which balances out to be, in this case, a little higher than they're supposed to be. So we're fine. So you can actually see that that's the entire joke. Like when a ship comes in and they're going to inspect the food, the USDA inspectors and everything else goes out there and inspects it, they're not inspecting every single box that's on that ship. They're just inspecting a few of them. And if that comes out to be fine, the entire thing is approved. Same thing as people are coming off the lines. They're not testing every single one. They might test one box a day. And as long as it comes out good, we're good. Oh, I did leave that on there on purpose. I was like, wait, I did leave that on there. That's fine. All right, let's look at this one. So when you're looking at these problems, that's all the information you need to pull out of them. X is 2,500? No. X is 29 minutes. That is N. My standard deviation is 8.5. What's my level of significance? Yep, 0.05. What is my null hypothesis? What am I comparing it to? $29.3. And my alternate hypothesis? Nope, remember, the null hypothesis and alternate hypothesis has to be the exact same number. The only thing that changes is less than, greater than, or equal, not equal to. In this case, they want to know, has it decreased? So it's going to be less than. Yeah, these two numbers there always have to be the same. Okay. Let's see if it makes a difference. So they've just reprogrammed all the lights. So let's see if it made a difference. All right, so 29.3 is my null hypothesis, alternate hypothesis. My degree of freedom is off the charts. My sample mean is 29. My standard error is my sample standard deviation 8.62. Oh no, 8.5. 8.5 divided by the 2500. And I'm comparing it to the plus or minus 1.6455. So my test statistic is negative 1.7647. So it falls inside the reject region. So I am rejecting my null hypothesis. So what does that mean? Okay, so they, by reworking the lights, they reduce the travel time of the commute. Right? So did they do a good thing? Okay. How much did they reduce it by? How much did they reduce the travel time by? Nope. Yeah, 0.3 minutes. So it was 29.3, and there it's now, it might not be exactly 29, but I know it's less than 29.3. How much is 0.3 of a minute? Less than 20 seconds. It's 18 seconds. Okay, they cut the commute of everybody by 18 seconds. Would you even notice that? No. Okay, so here is a very important distinction. Is it statistically significant? Yes, we proved that. That's what we just did. That's this test. That test shows it is statistically significant. Okay? And that's why we rejected the null hypothesis. Is it practically significant? No. 18 seconds, who cares? We spend longer than that waiting in line at Dunkin' Donuts. Okay? So sometimes when you do a project or your study and everything else like that, you get data that is statistically significant. But your results are so close that who really cares? Like, it's not practical in any way, shape, or form. So, well, yes, they will claim we've reduced traffic, travel time to work, and that's going to be the headline in the newspaper, but in reality, it's 18 seconds. And nobody's going to notice it. Okay? Why do you think it was such a small amount? What do you think attributed to me rejecting the null hypothesis and it really not making that big of a difference? What number seems out of whack compared to the other problems we've done so far? Yeah, they did 2,500 people. They had a huge sample size, which means that my standard error is really small. And that's why it pushed it over. If I had only done, say, 200 people, now it doesn't matter. we didn't reject it. Even if, I think even if I did 2,000 people, I wouldn't have rejected it. Because the sample size was so large at 2,500 people, it pushed it over into that reject, even though it really doesn't make that big of a difference. So, practical significance means that while the small differences between statistics is that it's not really large enough to be a concern. So we really wouldn't care about it. Large samples can typically do that. All right. 10.5. We only covered 2 of these. However, you also can have the standard deviation ones. This is one we did not cover. So depending on which ones you have your proportion, your mean, or your standard deviation. And we did these 2. We didn't do this one. So 10.5 should just literally ask you which process you're using. It should not make you do it, from what I saw with the problems. So you should never actually have to do that one, but you might have to actually label that as the null hypothesis and the alternate hypothesis, from what I saw in the problems when I looked earlier. All right. I should change the beginning of this problem to any governmental agency or any customer service department has been flooded with complaints. People must wait more than 45 minutes before seeing an IRS representative. To determine the validity of these complaints, the IRS randomly selects 400 people entering the offices and records the times they must wait before seeing an IRS representative. The average wait time for the sample is 55 minutes with a standard deviation of 15 minutes. Okay. So, first off, what's the population being studied? You haven't asked this question in a while.
400.
That's the sample. Huh? Not everybody. The people who are coming into the office. People are going to the IRS office because those will be the ones that are making the complaints. So not necessarily everybody in the United States, but people that are going in or trying to see an IRS representative or calling an office. All right, so let's pull out our information. So null hypothesis, alternate hypothesis. So what's my null hypothesis? "45 minutes. And what's my alternate hypothesis? Yep. More than 45. Great. What's my level of significance? Yeah, 0.1. Right there. What's my sample standard deviation? Or sample mean, sorry. "55. What's my sample standard deviation? And what's my sample size? 400. Good. All right, let's fill them in. So my test statistic is 13.33. I think it's higher than 45 minutes. It's so high that it doesn't even show up in my graph. So we reject. So is it statistically significant? Yes. Is it practically significant? Yes. I would say waiting an extra 10 minutes would be practically significant in this situation. Okay. So yes, this one would be both practically and statistically significant. All right, so dog food manufacturer wants to know that the proper amount of dog food is being placed in bags. So this problem is giving you your null hypothesis X, is giving you everything you need. Except for what level of significance is. What level of significance do you want to try it at? Okay, let's do 0.5. Correct. And most problems are going to give it to you, but yes, you can technically choose at that point. All right, let's see what happens with this one. 25. No, that's not what I wanted. That's 25.01. 21. I think we did 2,000 bags. All right, so my test statistics at 4.47, so it's way over here. And we are rejecting. Okay. So I've rejected my null hypothesis. Is it statistically significant? Yeah, that's why I rejected it. Is it practically significant? How many people in here ever bought food for a dog or a cat? Okay. How much would be 0.01 pounds of it? Yeah. Maybe a kibble or two. Like, yeah. Okay. Would anybody notice? No. So again, statistically significant, practically you could care less. And again, look at the sample size. 2,000 bags. All right. They basically did a whole pallet of the food at once. Okay. So not a thing that I would be worried about. All right. I didn't put the one on here from Hurricane Andrew. That's okay. I should find the. So, one of the problems that came up in my other class when I was doing this one was about Hurricane Andrew. So Hurricane Andrew hit in 1992, but before most of you were even born, and destroyed southern Florida, caused billions of dollars in damages. And it was at that point the most significant hurricane damage to the United States. And what it caused was that disaster, the average claim was higher than they would have expected. So insurance companies work on statistics. They determine how much things are going to cost based on mean prices, and then they add levels in there. So, like if they were looking at the mean was $25,000, they would do that significance level and go, okay, but I'm going to charge based on $26,000 because that would be a level of significance of 0.5, and I'd be fine. Well, Hurricane Andrew came in and kicked that totally off the charts, and they lost a ton of money. So what happened to everybody's insurance rates after that point? They all went up because now they have new data points. I'd be interested to see how far out the Palisades fires claims in California were in LA last year. How much that was compared to what the mean claim was before that point, and seeing how statistically significant, how far off it was. Because that's the next one, that the insurance claim was way above what they were expecting and caused a lot of major issues. So as we start seeing more and more of these situations, more and more insurance rates go up, as we've seen in some of the other examples that we've done. All right, we're done. You are officially done with statistics. Well, done learning new things. Two things. Make sure you get your projects done. I seriously hope you learned something new and got something out of this class, and that you got something that like made math a little more practical than normal, like the math class that you had. The survey is online in Blackboard for our evaluations. Please fill it out. I do actually read them. One semester I had a class that literally told me I gave too little homework. I decided to ignore that comment. But I do actually read the comments, and I do appreciate the feedback, so I can make changes going forward. So please fill those out. I will see you on Thursday for the review for chapters 8 through 10. You're welcome. Yes.
I'm confused about how to do it like in between.
Oh, use confidence interval. Use the
Okay.
confidence interval test. So use. Where was it? I think it was in this one.
Okay.
My glasses are in the student lounge, and that has my class pass.
You don't have a key to the student lounge, do you?
I might. My key might work. I'll be going over there in a second. Yeah, use this one right here. And it gives you both of them.
So, but what data? There was like, I think it's 10 too, maybe?
Oh, okay. I don't want to change this one.
No, that's fine, because it's just these will change. So
Yeah, okay.
just run to 10, because I think I was confused if it's the one. Yeah. There just wasn't enough. Like, I don't know.
So it gives you your sample mean.
Okay.
So you figured out.
And then what do I do for the size and deviation? Okay, 10. And then I think I used this and I put it in for a deviation. I put it into
10. Let's see. So 0.11. And
maybe try one of these. We'll already have the.
wait.
Right.
Oh, hold on. You have to figure it out.
Right. I think it's in one
Oh.
of these. This one, maybe? The end.
It is that one. Okay.
And then I use the sample.
Yeah, so mean is that.
Which the mean is also different from what they're saying. Oh,
Right.
because it's a sample.
Yeah.
I got it.
Yeah.
I
That's
got
you're
it.
not using that, you're using those.
Thank you.
You're welcome.
I'm there now.
Hey,
It's okay.
is it fine if I use AI to make my graphs for my project?
Um,